is brought by Salvatore D'Oro. Salvatore is a professor from Northeastern University. He will share the views on AI in ORAN. Thank you.
Thanks for the introduction, and thanks for staying out here. That's the last presentation, and they'll talk about the effort that we are calling OpenRAN Gym. And this is an effort we are doing at Northeastern University. And before going into what is actually OpenRAN Gym, I'll start saying why we have developed that. And I would say that probably there are 4 main reasons why we started developing this and as an open source effort. First, there are no experimental platforms that are end-to-end, and so meaning that they give you access to RUs, DUs, CUs, the base station, the RAN, the core network, and the SMO, and the RIC, and all those things, right? After that, it's not just that they're not there and they're publicly available, but they're not even large scale. So most of the cases they are lab set up. So you have like 1, 2 UEs, and then there is 1 RU, and that's pretty much it. The other thing is that if you want to work with AI, you need data, and there is not much data available. At least it's not publicly available. If you have partnership with industry that has the data, with operators, they have the data, they can give you the data, but the data just rarely goes out of their lab. So you access that with a VPN, and then the data is there. It's not publicly available. And the other thing is that there is a big lag between ORAN and OpenRAN in general and academia. And since AI is something that is kind of like requires a lot of innovation, we believe that we should kind of like fill the gap. So we have developed OpenRAN Gym. OpenRAN Gym is the first publicly available research platform for OpenRAN research. That's open source. You can find the GitHub repository there. You can access that. And this offers an end-to-end OpenRAN platform that gives you access to the RAN, the core, a neural time RIC, a framework to develop X apps. There is the E2 termination and the E2 interfaces there. And this all comes from the OSC releases, so we have extended those. So thanks for making those available to the community. We've just like an effort that we have done to kind of extend that. It also comes with support for network slicing. So basically, that's one of the use cases of ORAN. And it's integrated with Colosseum, which I will describe in a few slides. That's the world's largest RF emulator with hardware in the loop, meaning that there are actual radios transmitting actual signals, and you can access that basically for free. And it has all embedded the data collection capabilities. So where you can get the data, you can use that to train the AI, you can test the AI. So this is the architecture that we have developed in OpenRAN Gym. And it basically comes with a neural time RIC, which we call Coloran, because that's a neural time RIC from the OSC we have developed for Colosseum. It comes with a E2 termination, support for X apps, and all these nice features. Then we have the RAN and core components. For this specific effort, we are using, for example, OpenAir interface and SRS RAN. So thanks, Florian, for, again, making that available. We have extended those because they originally, there were some features that were not implemented, specifically they were not ORAN compliant yet. So we supported all the development to make those talk ORAN. And those are so accessible, and they're available to the RIC. So the X apps will be able to control a software-defined radio that is actually implementing a base station using OpenAir interface of SRS RAN. And that gives you the possibility to get the data from the E2 interface, right? And not only the data, but you can also do the control part. So you have X apps taking decisions, so you can use the E2 to enforce those decisions. And there is integration with a bunch of testbeds. So I've been talking about Colosseum, but actually that's kind of like testbed independent. You can use it with Arena, which is another testbed we have over the air using software radios, but you can integrate that with the Power platform, which are part of the Power program in the US, which are a bunch of testbeds, open testbeds distributed across the US. And I promised to talk about more what's Colosseum. So this is Colosseum. So this is a large data center that we have at Northeastern University. We inherited that from the DARPA Spectrum Collaboration Challenge. It's a container-based architecture, so a bunch of servers and 256 radios. Those are software-defined radios, meaning that they can execute pretty much everything. That you can use them as Bluetooth transceiver, Wi-Fi, 4G, 5G, 3G, 3G, 2G, whatever you name it, if there is a software stack that implements those functionalities, the radios will act as those transmitters. And it has three main components. One is the traffic generator, which is basically where you want to generate different traffic profiles. You can see that as a different class of traffic. It can be video streaming, it can be browsing, it can be emailing. You can generate traffic profiles that are specific to different slices. For example, EMBB, URLC, and MTC. There is another big component, which is the massive channel emulator. So Colosseum basically gives you the radios. There are 256 radios. Those radios are transmitting actual waveforms, but they're not transmitting waveforms over the air. They're connected with cables to what is called MCAM, which is the massive channel emulator. So you have an any-to-any RF matrix with configurable channels. So what we do, for example, we get GPS coordinates for actual base stations, for example, in Times Square. You get the GPS coordinates, you use ray tracing, you use channel sounding, you can use analytical models to define the channel, meaning you can specify the pad, the fading, the path loss, and all those sort of things, and that are executed in real time. So the radios are working in real time. It's not a simulator, that's an emulator with hardware in the loop. And then, of course, you have the radios, which, as I said, are programmable. You can instantiate open interface or SRS RAN. Now that we have ticked all the boxes, we can kind of like discuss how we can use OpenRAN Gym to develop X apps. So when you start working with AI, the first thing you do is data collection. So you need the framework to collect data, and OpenRAN Gym gives you the tools to instantiate the cellular network, start collecting data. Then you want to train the AI, test the AI. You want to compare different models. If you want to use deep reinforcement learning, if you want to use the deep forest, neural networks, whatever you want to use, you need that platform to kind of like test those different modules and their performance. Then you want to develop and deploy the X apps, so the AI has to be converted into an actual X app that can run. And then you want as well to do online fine-tuning, right? So you test an X app with data coming from Times Square, but you're going to deploy this in rural Arkansas. Traffic is completely different, so you want to start with an X app that is kind of like working pretty much everywhere, but you want to specify that for the specific deployment. And you do the online fine-tuning, and then you can measure the performance. And the nice thing about what we have developed is that it takes one line of code to instantiate the real-time RIC, one line of code to instantiate the G-Node-B and subscribe to the RIC, and one line of code to start any X app. So you basically get the X app, one line of code that works. And that's how the X app works. That's the template coming from the template from the OSC. We have kind of like divided it into two different components. There is the SM connector. That's where the E2 interface basically gets the data. And it's not just like getting the data from the G-Node-B, but sending the controls to the G-Node-B. And the other part, which is the inference part, that's the data-driven logic unit. So the goal is that you get any AI model, you plug it there, the AI model gets automatically connected to the SM module, which gives the data and basically provides the connectivity to the G-Node-B, and then that's basically how the template works. And this is a template we provide, comes from the OSC that's been actually customized. So you can get the template that's open source, you can integrate the logic, and then you can execute the logic directly on the Colosseum or any other testbed. And that's, for example, one specific use case. And this is a run slicing use case. So that's one use case specific to the ORAN community. As I mentioned before, the framework comes with network slicing capabilities. It's not specifically implementing the 3GPP network slicing functionalities like puncturing and that sort of things. But we are mimicking that by assigning, for example, the PRB, the min-max ratio or the reserved ratio for each of the slice. And the other thing we are doing, which is not in the ORAN use case, which when we talk to operators, they're like, oh, that's great. But when we talk with manufacturers, like, oh, no, we don't like that. It's the scheduling policy control. Because basically what you want to do with AI is not just assigning PRBs to the different slices, depending on the load, but you also want to say for each of those slices and each of those PRBs I have assigned, I want to use this specific scheduling profile. I want to be more aggressive, to be more fair. I want that to be round robin, to be best effort. So those are the different profiles, right? So vendors have their secret sauce there. They have different scheduling profiles. But if you can select a different profile for each of those slices, that's what the AI is doing. So what we have been doing is to get the data. We have trained a deep reinforcement learning agent that not only assigns and slices the PRBs, assigning PRBs to each slice, but also for each of those slices assigns a different scheduling profile. And for example, that's to the left. I don't know what you can read there, but that's the actual implementation. For example, we are using autoencoders to create a latent representation of the state, because you have a lot of this data coming from the G node B, and that's too much data for an agent to process. So you want to compress that, and that's what the autoencoder is doing, creating like a virtual representation of the data that is easier to interpret from the agent point of view. And then you have the actual agent that takes the decision, and the decision goes back to the connector, and this goes back over the E2 to the G node B. And in this case, we are just showing like a very quick result. So we have 3 slices. This is one slice that's a MBB, that's video streaming that needs high throughput. And we have 2 different slices, which you can see them as best effort. That can be, the nice thing is that can be just one user, or it can be a class of users. So you can have this customization available. You can select which UE will actually belong to the specific slice. And when we start the XApp, you see that throughput, I don't know if you can see that, but here where there is the blue line, once we start the XApp with that line of code, we get the data over the E2, and you see the throughput for the EMBB slice jumps up. And if you see, each of those pictures is a different testbed. So that's the same XApp trained on multiple data from different scenarios, executing on different testbeds, with different radios, with different channel conditions, and you always see the improvement. So we have tested it on Colosseum, Arena, Powder, and Cosmos, which are power platforms. Those are over the air. So that's actual data coming from the G node Bs over the E2. AI is taking decisions. Without doing any retraining, you see the improvement. And another effort that we have co-developed with Mavenir that we are trying to contribute to the OSC upstream is what we call the NS ORAN. That's an integration of NS3 and the ORAN neural time REC. So basically what is missing is that the neural time REC works in real time. NS3 is an event-based simulator, so they are not kind of like speaking the same language. So what we have done is to develop an let's say an interface, which is the basically E2 SIM interface, an extension of that, so that you can use your actual neural time REC running in real time. And you can plug it to NS3, which does the emulation and simulation for you. So basically, you can use that to test different use cases, develop XApps, and see how they behave in the wild on the real-time REC, but actually using the NS3 simulator. And that's a different, this is simulation. OpenRAN Gym is instead tailored to emulation with the actual hardware. And this is, we are trying to push it to the OSC as well and contribute to that. And that's pretty much all. So thanks for listening. I don't know if you have any question.
Okay, thanks, Professor Salvatore, for sharing the AI experience in ORAN software community. Now, the next is the Q&A slot. Welcome all the speakers. Okay, thanks all the speakers for the great presentation. So is there any question or comments on today's presentations?
I have a question to Florian.
Yes.
I know there was some great work that Robert Schmidt did on the WIC implementation, this 5G mosaic, and I like the approach that he did there because it kind of simplifies the whole. It's a library approach, and it kind of simplifies the implementation of the WIC. Lots of complexity is moved out. We can very easily develop an XApp. But now you say you are planning to evolve that further. Merge it with another implementation. Can you shed some light on what you're planning to do there?
That's an excellent question. I can't give you any technical details because that's not my area of expertise. But I mean, thank you very much for your comment on the on the flex rig. I'll forward that to him. But it's important for us that we are interoperable with other rigs too. So in that sense, we need to make sure that we can talk to those other rigs as well. So I'm not familiar with the technical details, what is needed exactly to do that. I know that today we have these 2 flavors, but we need to converge to one. So that's actually an ongoing discussion in open air how we'll get there. But if you have some inputs, I'm glad to hear them.
Sure. Maybe one more question. That's about, you mentioned this paper about the TDD uplink frame structure.
Dynamic TDD, yes.
Yeah. So is that about actually changing the frame structure as you go? Because that normally, because of interference, should be the same between all operators. So
yes.
What are you doing there? I could read the paper, but
yes.
I wasn't that
No,
fast.
I'm aware of the fact that dynamic TDD is not easy to deploy because of the regulation. Because if you have different TDD patterns between operators, you have interference. So, but that is not. We kind of ignore that fact in that paper. It's a more academic paper. So we really reconfigure TDD, and it's the semi-static TDD configuration. So we send a new TDD configuration over RRC to adapt to the traffic environment.
Okay. Thank you very much.
Okay.
Good morning. Question for Salvatore. In Orange, we are developing some machine learning framework based on public clouds, and one of the challenge that we have is to let's say test or develop and test these machine learning algorithm before putting them in production and kind of secure them and manage conflicts between different apps and so on. So we are trying to create some development and test environment where we can, let's say, make this secure the behavior of the algorithm before putting them in probably small scale and then larger scales. Do you think that your project, that to be honest I didn't know and I found very interesting, could be, could take some role in this challenge?
Yeah, so that's actually one of the reasons why we have developed that, because we do a lot of research on AI, and most of the time AI, especially during training, it takes decisions are very bad, and you don't want that to happen on the production network, and the framework has been designed exactly to prevent that. Offer a tool that you can test the AI in different deployments, so you might find out that you have 5 deployments. In 4 deployments, the AI works fine, but there is that 5th deployment where the AI takes always bad decisions. And that's basically the idea of taking the XX apps or the AI from the external world, bringing them to the neural network rig we already have, plug it there and see how, and test those scenarios beforehand and see how the X apps behave, if the AI has to be fine-tuned or has to be retrained and those sort of things. Yeah, and there are, of course, like, for instance, we can discuss how to access this.
I've taken some photo.
Yeah.
But I don't have your email address, so
yeah, we can get in.
Follow up that
Yeah,
video.
sure.
Thank you.
Thank you very much. I have a general question based on the title of this session, which is ORAN being accelerated using open source. And I'm addressing it to anyone who wants to answer. The different initiative in open source that we are experiencing today, we have many different implementations of open source for different areas. Having these different flavors, is it helping, or is it actually a challenge that is slowing up the process of adoption?
I think for this question, maybe our speakers can share their views from different angles.
Maybe one of them also
Yeah,
exploited in
one
their
by
products.
one. Yeah, just share the views.
Sure, it's different ecosystem have different views and different opinions. Okay, and this is the whole idea of open source. It's that you have multiple projects, and it's based on contribution. So if a certain way it's, let's say, more popular, it gains more momentum. Okay, so yeah, I'm not going to disagree that there is a lot of redundancy, but And the community is always trying, for us specifically, this is why in the ORAN software community, we could have went and created a brand new infrastructure project and said, no, there is already one that addresses maybe 90% of what it's needed. Let's use it and expand on it, okay? But if you're really, but not always it's as simple, let's put like this. But yeah, it will be better if more join to drive the same thing. But there is also different focus areas. So if you're looking, for example, Sterling X versus the larger CNCF, the larger CNCF focus on enterprise primarily. Okay, there is unique problems that basically the telco market requires. And this is why when Sterling X was created, basically was, the community, especially at the time it was the OpenStack Foundation, now it's called the Open Infrastructure Foundation, was looking specifically and saying, okay, can this done in the bigger enterprise side? And basically the determinism was no, it's like there is specific issues and you just get them diluted in the bigger enterprise because it's based on contribution, based on how many participants, and it's always getting a second priority. So is there some overlap? There is some overlap, yeah. So this is why if you look at, for example, Sterling X, it has two parts to it. It has an integration part and an IP creation part, okay? So meaning the stuff that is specifically relevant to the telco, it's called it as an IP creation. And the integration part, it's downstreaming from different projects and expanding on it and then working with those other projects to upstream it.
Okay, thanks, Gio. So
I just wanted to add, I think I was also mentioning about that MVP in my thing, and just today I learned that, the OpenRAN Gym offers a very good testbed with live data that's coming in, and RNA networks as an SMO layer, which seems to be more functional than what is there in the code right now. And we can, and Wind River has a great O-Cloud platform, right, that they're giving. And so if you connect it all up and come up with an MVP, that will be a very great story there, right? But I think that's still coming in the next releases maybe, but today is a big eye-opener for myself because we have been focusing on just the near real-time rig and the sandbox that we are working with. But if I look at today, we have a lot more things to integrate, and we can take it further along. That will give the power of the MVP truly, right? Like I said, aggregated across the architecture and tier layers. And I definitely look forward to that. And I guess if you do that, that would make address some of the concerns that you are talking about. And of course, there is always duplication, and the best one will win. But we have to synergize and integrate all these projects together to get that maximized. I'm definitely looking forward to that.
okay, thanks, Ramesh.
Thank you. Yeah, I will just add one point over here because, representing ORAN SC, the open source anyway, I think at least from its early stage, we definitely welcome more open source implementation. It means, you don't know yet how the architecture and all the implementation use case evolve, right? So you may want to have as many contributor as possible. For example, as I know, for the near real-time rig today, there are at least a few open source implementation over there. But once the ecosystem reaches to a critical mass, maybe it means all the architecture as well as other the details are nailed down. Then all the open source may just work towards the same direction, and they kind of converge into the way it's supposed to go with. So that's my point of view. And at the same time, even for OSC, in the past year also, because of the different implementation for the near real-time rig, right, we were making certain efforts to say, how do we have a cross-platform kind of SDK to ease the development? It's like at the same time, we want to have maybe a unified way, right, across the open source community to make it easy for certain implementation or development going forward. Thank you.
Thanks, James. Pavel?
To answer your question, I see that as a strength rather than a weakness. Okay, the reason being, as many of them mentioned, like, the industry is maturing, right? So, and different people will have, like, different use cases to cater. So right now, we don't know what use case can cater what scenario. And in the world of this collaboration, so there is this, the side effect of, like, the duplicate features or duplicate code happens, but over the period, I see that, like, things will consolidate and they will emerge as, like, a matured product. So this is kind of the journey. So in this journey, as you mentioned, yeah, these things happen, but these are part of the game. So that's my perception.
Okay, thanks, Pavel. So how about William Stigl?
Yes, this is something interesting because I think something key is the cross-community coordination, that it's something implemented in most of the open source communities today. And this coordination is key because it allows to different projects to focus and avoid overlap on the different aspects of the implementation of technology. For instance, the coordination between the ONAP community and the ORAN software community is important because the ONAP community is focused on the general overview of the orchestration and so on, and the ORAN software community implements part of, or use part of the code of the ONAP in order to implement the SMO. So this coordination helps the ONAP community to improve interfaces needed by the ORAN software community, and the ORAN software community upstream that code based on the development doing in the ORAN software community. So this is one example, and I think most of the open source community try to have this cross collaboration in order to improve based on the different scopes that each community has. Yeah.
Okay, thanks, Williams. So our two professors, is there any
No.
views on it? Okay, thank you. Thank you, everyone, for attending this session. And we are looking forward to more contributions to ORAN software community. Thank you. Okay.